Congratulations. Just getting the YouTube stream up. Why don't I hear music? Is it just that quiet? I hear music now. Okay, it was quiet. Okay. YouTube stream's up. Ah, my whiteboard looks so tilted. Hey Zach, how's it going today? I'm just gonna leave my whiteboard how it is. I would play around with my phone so much trying to get it at an angle where the whiteboard isn't like slanted, but I just could not do it today for whatever reason, so I'm just gonna go with it. Okay. We'll do the traditional kind of filler abstract algebra stuff in the meantime, because I don't think there's anything in my Discord. And I don't feel like looking on the internet for something in my Discord that I can help with anyway. And I don't feel like looking on the internet for questions. Hey, SBQ. You now officially have your coursework finished for the PhD. Only the dissertation is left? Oh, awesome. So, if I remember right, okay, so I knew that you're close to getting a PhD. I thought it was like the normal kind of circuit. It's like 2 years of coursework and then potentially 3 years of dissertation, or is it like 2 years of coursework in 1 year of dissertation? Your last grade posted last night. Oh, awesome. I honestly, I can't remember. I thought it was like 3 years of like working on the dissertation part, but it's been so long since I've looked into it that I don't really remember how it works anymore. Depends on the program. Oh, okay. Where was I in the book? Finite groups and so wait. Yes. Spend all your time on the dissertation. Okay, nice. That's pretty hype. Sounds like you'll have a lot more flexible schedule too. I'm sure it'll be nice with the stream. I mean, you're not streaming yet. I think I was thinking about 49, but I didn't actually do it. Oh yeah, I remember starting to do 48, but I was way too lazy because I got the idea of it, and naming the actual groups and proving it was super annoying. Yeah, for 49, I'm still a little stumped on how we would do this. A group of even orders with an odd number of elements of order 2. Yes, I think we were exploring with this one. But at least I wasn't able to get to an actual conclusion here. Or get like or even start on a proof. So I want to look back maybe through some of the other exercises. Think you have an idea? Oh yeah, please let's hear it, SPQ. Because I'm just like, all I'm doing right now is looking back at some of the previous exercises to see if there's like some inspiration or something we can use from these, but I think I already tried that once and it didn't, I don't remember seeing anything like. Consider a set of pairs G, G inverse, okay. Untextured size, this song is called. The hell? Size in like SIGH. Odd number. Because when it's an odd number, I have difficult times. You can't necessarily just make pairs as unless you reverse it and you say that there's an even number of elements not order 2. That maybe can make pairs with that, but I don't know. That doesn't. You have to do a bit of extra work there if that does work in the first place. But there are 2 cases. The order of g is less than or equal to 2, and the order of g is greater than 2, including infinite. If the order of g is less than or equal to 2, then g is equal to its own inverse. Yeah, because order 0 doesn't make sense. So g would either be self-inverse, where g equals g inverse, or g is e. Okay. The number of elements of G with these pairs. Hey, Phobos. Oh, that's an adorable emote. Is that new? I love it. You made that? I didn't know you could do art. Yeah, that's awesome. Do art, draw. Yes, I do art with great effort and frustration. That's fair. SPQ is saying become the number of elements of G with these pairs. You count the number, so we're how do we count the number of elements of G with these pairs? So like you're saying, like, you know, we have a tuple like E comma E, G comma G for the self-inverse ones, or, you know, order 2. The entire group is even order. Divided into 2 sets. And we did, I mean, I don't know if it'll be helpful, but we did prove that that will be a group. At least individually. If you do like multiple ends, I don't think that works. But at least for a fixed end, it does. I think that gets messy though for B. Maybe we shouldn't worry about calling them groups. It sounds like it might not be necessary for your idea, SPQ. So would the task be then to show that A has an even, I guess, cardinality? Because one of those things is going to be E. So if you remove E from A, then you have an odd number of elements. Hello to AS Gaming Bros on YouTube. How's it going? That's at least like, I guess, something to chew on, but I guess I'm still not sure how we are fundamentally answering the question. Like, how would we go about counting A or counting B? Or, okay, well, I mean, just thinking about A, how would we show that A has an even number of elements? Good, good, actually. That's good to hear. Hmm. Woohoo, hey! Yeah, I've been trying out this, like, piano playlist the last two, like, math streams. Um, I've been liking it. So sometimes it's a little too, like, low key, but I feel like my other playlists are getting a little old, so it's nice to like mix it up when not do an example. Yeah, I was thinking like in chapter, I always forget what chapter I'm on. In chapter, whatever the chapter before this one is, we talk a lot about like the order of like I think like U4 or something like that. Even it's an even subgroup and like E's order 1 and the other 3 elements were all order 2. It probably wasn't U4 though. It was U8 or I don't know. Let me. Which one has maybe 8 things in it? You could do U20, yeah. Could get spicy. Well, I'm not opposed to a little bit of spice. All right, let's go with U20 and see. Make sure it has even order and then verify that we do have an odd number of elements of order 2, and maybe think about why it can't have an even number of elements of order 2. Actually, wait. 20 is going to have 1, 3, 7. Wait, why did I start counting from my thumb? I never do that, but okay. 1, 3, 7, 9, 11, 13, 17, 19, which is 8. Okay. So U20 would meet the first part of the if. I never knew that like I think in like Germany and stuff they start counting on their thumb, and I never knew that until the movie Inglourious Basterds had like a whole thing about that. Where the Americans had to like make sure like they're going undercover as Germans, they had to make sure that they would count on the right fingers or something. It's a good movie. It's one of my favorites. So U20 is 1, 3, 7, 9, 11, 13, 17, 19. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. The order of 1 is 1. I feel like I've done this before, but it'll probably be helpful to see it again. 3. 3 times 3 is 9. 9 times 3 is 27, which becomes 7. And then 4 gets us where we want to be. 7 times 7 is 49. That becomes 9. 9 times 7 is 63, which becomes 3. And that gets us where we want to be. 9 times 9 is 81. You are self-inverse, my friend. 11. The element squared is 121, so that's... Oh, that's not order 1, it's order 2. Order of 13 is the same at... Okay, 13 is the same as negative 7. We're going to need to use that now. So negative 7 times negative 7 is 49, which becomes 9. 9 times negative 7 becomes negative 63, which is 17. 17 is the same as negative 3, so negative 3 times negative 7 is positive 21, so we get 4. Eventually, Fenbox's advice to start using negative numbers all the time with modular arithmetic sunk in. I remember the first time I did this question, it was I only did it like half the time, and it was bad. Okay, so 17 is the same as negative 3. Negative 3 is 9, is still 9. 9 times negative 3 is negative 27, becomes 13. 13 is the same as negative 7. Negative 7 times negative 3, okay, so you're 4. Okay, and then 19 is the same as negative 1. So you have order 2. Okay. Make sure chat isn't melting down. Okay, good. We're fine. So 1, 2, 3 elements of order 2. So it is odd. It's both weird and odd. So I guess I'm looking for I'm still looking for symmetries. We can notice, at least in this group, 9 and 11, oh god, are in the middle. And then 19 and 1 are at either end. And the identity must be like related here. Hard locked. Husky screaming for no reason is never like not going to be funny. Thank you so much, Hardlocked. And yeah, you know, I agree. You are first. Hey, Stooky. Good morning to you too. _ hate. Looks so cute when you're thinking and calculating for your mind. Because it's good advice in the chat history. Find step B things with order greater than 2. Yeah, It seems like it's getting a little like tricky if we think about what's not in the group of the question asked, but maybe we just need to wade through that trickiness. In Begula, did I say hi? I already forgot, but if not, then hi. Hardlocked, I appreciate you. 17, the absolute value of 17 doesn't equal 4. Dude, modular arithmetic, some of the things that you say when you're doing modular arithmetic like make me deeply uncomfortable. Like that order of 17 equals 4. It's not the absolute value. So the group has even order. Modular arithmetic. Like, I'll spell it out. Where the mod is, it's like division, but instead of doing the actual result of the division, you return the remainder. So like, if you remember the first time you're taught to like divide numbers, you probably are doing it with remainders. The mod gets you that remainder rather than the actual result, and it gives you all these weird things. Arithmetic physics. Oh yeah, you shouldn't need modular arithmetic for that, but yeah. So if we do want to go down SPQ's path here of looking at the things that are order more than 2, we would want to show that there's an even number of things more than 2 because the entire group has even order. E is always in the group and always has order 1. Yep, but big, this is a good time because I'm trying to stall to think right now anyway. But I'll show you quickly a bit more what the mod actually is. So like if you like what I was doing with like 17 is if you do 17 mod 20, you do 17. Oh, that's a 17 by the way. 20 divided by 17. So 17 goes into 20 once. You do 17 minus 3. So you get 1 remainder 3. And for mod, you care about the remainder instead. So you'd say this is equal to 3. And then I took that 3 and multiplied by 17 again, and then did mod 20 again. And I did that again. Instead, I used 4 17s. I said that in this context with abstract algebra, that the order of 17 in modular arithmetic is 4. Because you do 17 times itself 4 times to get back to 1. If you know computer science at all, it's often represented with like a percent sign too. Like that. Stuckey sees the plan. So like, sure, we can follow SPQs. Or, you know, we can name the A and B that SPQ outlined here. My issue is I don't see what we do after this. Basically, the task would be to prove that for a group of even order, half of it has more than order 2. I don't see a particular, yeah, I don't really see a particular, like, there's the symmetry where The 3 and the 7 are in the middle, and the 13 and 17 are in the middle of 1 and 9 and 11 and 19, but is this like the medium thingy? I don't know what the medium thingy is, Bigula. Which things are inverses of each other? Draw some arrows. Really? Well, 3 and 7 are inverses. 9 and 11 are both self-inverses, so I don't know. I'll try arrows like that. I assume 13 and 17 are it's same as 7 and 3. Yeah. The 19 is self-inverse. I mean, this is kind of... I feel like I'm not saying anything new. Like, if it's order 2 or less, it's going to be self-inverse or the identity. Are there other... No, the inverse is unique. Are we making some statement about how it's even, so the order must divide 2 of each of these? Or like the order of each of the elements must... Well, no, that's not necessarily true. Yeah, this is just weird. I don't know. Things that... Oh! Oh, okay. Well, I think I see the idea as Phobos says it. For the equivalence relation thing, I think it's saying basically the same thing in a different way. So... Well, we have to exclude the identity here for B. Actually, yeah, I mean, I should just say how SPQ said it. Less than or equal to 2, greater than 2. Okay, so, okay, this is actually a lot simpler than I thought. Let B be an element of B. Since the order of B is greater than 2, B does not equal B inverse. Well, B isn't a group. We don't have to have an inverse in B, do we? I think we will have an inverse. No, I think we're okay. Because it does come from a group that does have inverses. Yeah. So maybe we should make a statement that okay, yeah, this is how we fix it. However, the inverse does belong to B also, because the order of B is equal to the order of B inverse, so it must be greater than 2. Okay, so that's how we can prove that the inverse is in, that both B and its inverse are in B. So so all elements of B as a pair, B comma B inverse. Therefore, B is even. Or therefore, the cardinality of B is even. Since the order of G is even, the cardinality of A is even. I should have, I wrote out the word card. And now the idea is if you remove the identity from A, implies there is an odd number of elements of order 2. Okay, there. I think that will be my proof then. How about I actually see the idea after needing it like spoon-fed to me? Oh, underscore said B does not have E. I think that was when I was like the first version that I was writing. Create an exercise value even if it isn't a group. Do you remember what the exercise was about more? Because I don't remember that. Yeah, we don't need A and B groups at all for the sake of this proof. You're right. Oh. Yeah, I guess I was just being careful about not treating A and B as groups. Because, I mean, I guess A is a group. Oh, A might not be a group. Could it be, though? Maybe it is a group. No. It's not a group. Come on. Okay, no worries in SPQ. Yeah, it's always hard, like, because I simply don't want to look at chat sometimes so I can work through the problem for myself, but then when I come back and catch up with chat, I don't know what's old news or not. A can be a group, but B is never a group. Okay, that's fair. So yeah, B is never going to have the identity as we've defined it. Hey, Christian, FR. I never remember the dimensions. I can measure it for you quick, though. Let's see. This is just a wiper that I bought off Craigslist, so it's nothing special, but... I don't know if you prefer inches or centimeters. It's 47.5 inches wide, which is also 120 centimeters. And it is 35.5 inches tall, which is 90 centimeters tall. So there you go. I'm gonna put my mug away. 1 second. Okay. No worries, and welcome in. So thank you very much to SPQ and for Phobos for the help on that one. Does your answer surprise? Okay, I want to see what 50 is. I don't know if pens are assigned or not, but I'm kind of curious about this one. Consider the elements. A is this, B is that from... Oh, I guess, yeah, the determinants are 1. Okay. Find the order of A, the order of B, and the order of A times B. I feel like this is... My guess is that since they say surprise... the order of A, or the order of A times B is going to be the order of A times the order of B. And I bet that's just a special property of SL. That's my bet. I don't know if it's going to turn out to be right, though. $12.3 burritos tall, 31.41592. That's almost pi. Actually, no, that is pi. Just move the decimal. Beer mugs wide. How many bananas wide? Oh my god. 0.6 metric dawns by whatever. It's interpreted as a command? That's weird. Yeah, I would say this is about 0.125 football fields wide and 0.089 football fields tall. So we're using stupid American measurements. It's about the wingspan of one bald eagle by maybe 2/3 the wingspan of a bald eagle. Which I feel like a bald eagle's wingspan is probably like way bigger, right? This thing's huge. Okay. So A is 0, -1, 1, 0. B is 0, 1, -1, -1. Okay. So to find the order of A, this is SL, but I don't think SL has any. It's special to find inverses, or you get to save some work. I don't think you save any work with matrix multiplication though with SL, so we're gonna have to do this the old-fashioned way. Which, these are pretty easy matrices to multiply anyway. So let's see what we get here. -1. That times that. If I don't do these hand moves, I really cannot do matrix multiplication, so. Okay, there. It's nearly the identity. Really? Ugh. Really? That goes to 0? That's not good. What is the order of A gonna be? Oh, I think it's gonna be order 3? No? What are we gonna get here? Oh, okay, here we go. So we use 1, 2, 3, 4 A's. So the order of A is 4. Is self-referential lambda a thing? Like the lambda statements or whatever? I remember like barely learning about those in my computer science class. I forget what they're called. It's some really fancy thing where you like make a class inside of a single line of code. Yeah, that might be something else though entirely. All right. I did give myself a room to get to do the order B over there, so let's go over here. Times that. That times that. That times that. -1 plus 1 is 0? Last I checked. And that checks out with still being an SL. Okay. Ooh, is this only order 2 for B? Sure is. Okay. Then let's find out what AB is. That is, oh, are they going to be, is AB going to be the inverse? Or like, are they inverse of each other? Wait, that should break math though. I don't know. Let's just do the multiplication first. Sorry about that part later. Okay, no, we're not getting the identity. Never mind. 1? I think that's good for AB. So let's find out the order of AB now. 1, 1, 0, 1. 1, 1, 0, 1. Two. That worries me. Are they gonna have infinite order? Is this, yeah, the determinant's still 1. Interesting. Let's see. I mean, we got to do it again, but if everything else stays the same, this will just increase by 1 each time, which I think is what's going to happen. That's definitely not what I was expecting. So yeah, that's 1. That becomes 3. Becomes 0. Yep. So the order of AB is infinite. It's going to constantly, if you keep multiplying by AB, that upper right element is going to increase by 1 each time. Yes, G1. A equals I when you build C with matrices? Are you talking about like the coding language C underscore, or is that some other C? See the complex numbers. Oh, okay, okay. Sorry, I was getting caught up in like the C++ chat too, so I was like curious to see. See the complex numbers. If you build C with matrices, the matrix A that they gave us is the same as I. Really? I have no clue how that works, but I believe it. Is it because you like have... No, I don't know how you build complex numbers with matrices, I guess. Bringing up the reading group. So we just did 50 for fun. Oh, it was assigned, so... Okay, so 51 through 54 is next. So 51 here. Let A be a group element of order n. Suppose that D is a positive divisor of n. Oh god, what the hell does this mean? Let A be a group element of order n. Suppose that D is a positive divisor of n. Prove that the order of A to the power of D is equal to n over D. So D is less than n, or equal to. Wait, if D equals n, isn't this saying that A is the identity? I don't know. It's order 4 like I, but more precisely, if you look at the matrix's linear map, sends E1 on E2 and E2 on negative E1. It's an 90-degree rotation in the real plane. Multiplying by I is in the complex plane. Oh! That's super weird to think about. That multiplying a complex number by I produces the same rotation in the complex plane as multiplying by A does in the real plane. So you consider them equal? That's super weird. Kinda, yeah? Okay. You know, I think kinda is the best that I'm, you know, I just be happy with getting it kinda. Let A be a group element of order n. Suppose that D is a positive divisor of n. Prove that... Wow, okay, this is crazy. The whole D equals n case is kind of weirding me out. If you land on a matrix of finite order in GL and Z, its order can only be 1, 2, 3, 4, or 6. Oh, but it could be infinite. But you're saying specifically for the finite order ones in GL and Z. Huh. That's kind of crazy. Okay, I think I just need to start writing things down here for 51. So I once I kind of put the facts out in front of me, maybe I'll have an idea of what to do here. But I'm getting a little like bogged down trying to do like mental math on this. Let the order of A be n, and let D divide n. It's kind of strange that this would be true, to be honest. No need for anything terrible. Oh, you mean for that C++ thing, okay. With me, there's always a need for something terrible. So if the order of A is n, that means A to the n equals E. Oh, duh. So the case with D equals n doesn't actually... it's completely fine. This is what I was giving myself on my in my head. On my head. Do we want to like multiply each side by a to the negative d? That's what my instincts are telling me right now. I have a hard time explaining why though. Like, what do we do from here? because the order of D inverse is the same as the order of A to the D, the order. So can we figure out what the order of A to the n minus D is? Should we... What's the first thing you do when the question is prove x has order m? Then is it enough to prove it? The first thing you do... Well, you look at what A to the D is, right? Oh. Wait. Okay, maybe this is really simple. Okay, well, that's... Like, this just implies that A to the D is... Is this... I guess this is enough to prove it? Almost dropped my marker. That's my drop my marker. I was tempting fate by tossing it again. Okay, I guess that's good enough for me. I thought... No? Why is that little bit of hair, like, curled out? Okay, fine. What else do I need to do here? Is there a special case I'm not thinking of? We know that n over d is an integer. We know that d isn't equal to 0. E to the 8 equals e. Do we have e of order 8? Okay, true. Proving that, so, okay, true. We need to show that n over d is the least exponent that gets us e. I feel like I've had this issue before of trying to prove that it's the least one, and it's always been weird. How do we do that piece? So we could suppose there's a number less than n over d. That it's the order of A. We should know that it divides n over d. I don't know, let me just start writing things down, I guess. Suppose the order of A to the D is m. God, n over d. So I'm gonna have to use our assumption, or to use like the information given in the problem to get the rest of the way here, right? Since A to the since A is order n, can we make some point? Oh God. I was thinking making some point of like a to the 1, a squared, dot dot dot, a to the n minus 1 are not equal to e. How does this help us get to n over d though? Because n over d is somewhere in this list, so what am I really saying here? And like, if this is true, then why is this thing also true? It almost seems like there's a contradiction there. Except, I guess, a to the d locks us on to being on multiples of d. Sick marker throwing. Thank you, Bagula. M is less than n over d. Oh, sorry, that's what I meant. I mean, that's what I mean by m divides n over d. Can I combo diffie-q solving methods together? I mean, I don't see why not, Oak Spirit, if you're careful about it, but it's, you probably, hopefully don't have to do that. Okay, we can say, so I don't really know what's going to be helpful here or not. N over d. Well, to me that was kind of like it's an implication, but I can actually say it. I mean, I don't know if this line helps us either. Yeah, I don't know how we do this. Like, we can't just say that a to the m is somewhere in this list, so it's not e or something. Because what about a to the d? Like, a to the d is in this list too, isn't it? Well, or is it? Yeah, it should be. Yeah, it is in this list. Can you check if a to the d being order m can still be possible? I mean, this is like if m is less than n over d, I mean, I can't think of a real argument for why this breaks. I know that m would have to be n over d to get us to use a to the n equals e, but like, that's not, like, I don't feel like that's actually proving it. dm is less than n? Sure. Oh. Oh. This is a contradiction? Well, isn't nd also less than n? Or is it like n over d is also less than n? This is why I get tripped up on everything that I've been trying in my head. Like, I don't know. I mean, like, I guess I see how this works, but like, I don't see why 8 to the d with n over d is special, I guess. Like from here, like I would say, so it must be that m equals n over d, but this is, I guess it's, I guess, okay, yeah. I guess here, I guess it's special because we would have an equal there rather than less than. I guess. I don't know, dude. This section of the proofs for order just fucking confused me. Hey, White. 670 a group of STEM-leaning students hyped about sigma notation and partial sums. Well, I'd say the best thing about sigma notation and partial sums is you get to take super complicated problems, not care at all about anything that they're saying, make a series that represents it, and just numerically calculate what the answer is without having to do any actual like difficult math. They let you circumvent a whole shitload of super complicated algebraic complications because you just get to manually calculate things. And if you use a computer program, you don't have to actually do that much work. That's probably my 60-second sell for sigma notation and partial sums. Yeah, like Oak Spirit says, they're basically like programming. Now, you can do super complicated algebra with sigma notation and partial sums. Well, I guess not partial sums. I mean, you can, but it's not as helpful. But yeah, for partial sums specifically, that's my like selling point, I guess. Then I break math. Yeah, I guess so. I guess because we were working through them, I feel like a monkey with a calculator. Yeah, I mean, parts of like that, I think they use a ton in like engineering or things where you really only care about the end result of the number being within a certain amount. So being a monkey with a calculator is kind of perfect. Also, what does that say about engineers? Okay, that's a nice way of saying it, underscore. Where we found an integer, n over d, that gets us to e. So we know that the order of a to the d is less than or equal to n over d, and we eliminate the less than case. Space monkeys. Yeah, fair enough. So I think we're doing 51 through 54, so we gotta go down the list here a little bit. Give an example of elements A and B from a group such that A has finite order, B has infinite order, and AB has finite order. Ooh. I assume we're going to need matrices here. Because it's kind of sandwiched in between a bunch of questions about matrices, and the only thing I can think of where you have... I mean, they just made us do an exercise up here where... Wait. Can we just use this example back at it? Because A and B were finite, but AB was infinite. So can we take AB as an infinite? Oh, no. I think we can. We just need to be careful what we choose for, like, this AB and AB are going to be different from the AB and AB down here. Like, so B has to come second. B has to be the infinite one, which was AB. So we want to choose this A to be a inverse from here. And that'll get us to B, which has finite order. And hopefully, yeah, A inverse has finite order because we proved that A has finite order. Okay, let's actually show that. I can even have another example of groups that would have properties like this either. Man, 50 takes up so much room. I'm not going to show it. Okay, so back to red. So I was going to take... Okay, let me do like a little like separate area up here for 50. In 50, A was 0, -1, 1, 0. B was 0, 1, -1, -1. And AB, we said, wasn't it like 1, 1, 1, 0? Or I didn't say them in the order I usually do, but let me just re-multiply them. 1, 1, 0, 1. Okay, right. Then we're now on 52. So wait, the order of A, I believe, was 4. The order of B was 2, and the order of AB was infinity. Just make sure for B that that was order 2, because that'll be easy to verify. No, did I have it backwards? A might have been order 1. No? Or order 2. Wait, is B order 2? The math isn't working in my head. I'm not getting... One of them was order 2, I thought. I swear it was B. But I'm not getting the right result when I do it back in my head. Or... The -1 right there is what's... That's what I was getting. Were they both order 4? I thought one was order 2. Ooh, excuse me. that with that. That with that. B is order 3. I think I said it was order 2 and I made a mistake. I mean, it only matter for finite or infinite, but I think I wrote that B was order 2 for some reason. And I think I forgot to double count the first row in my math. Okay. So in 52 now, we want A finite, B infinite. And AB finite. So the infinite one here was AB. So down to 52, let's name B as 1, 1, 0, 1. And so B's are infinite. On the left, we're going to multiply an A. Which I think if we're going to have, you want to left multiply by A inverse, because it'll have the same order. And this is SL, so the inverse is relatively easy to calculate. You flip those corners and negate the others. We've already shown that elements in their inverses have the same order, so I'm not even going to check that one has order 4. Now let's test what what this AB comes out to be. So 0, 1, negative 1, 0. We should get like that original A back, or no, the B. We should get B. Off to a good start. 1. Perfect. Which is order 3, we said. Okay. So yeah, it's good that we did that one up above. Hey, Harambe. Yeah, this is it's abstract algebra, but this particular problem relies on doing some linear algebra stuff. It's part of an abstract algebra book, but matrices, you know, you can have a group of matrices that we were just looking at for, well, you don't have, for 52, you don't have to look at matrices, but it seems like the most natural thing. Hey, Fembox, how's it going? So thankfully we did 50 before this, because it basically gives you the answer 52 if you're going to rearrange your A's and B's and AB's. So we're going down the list up to 54. So 53 is what we're going to do next. So the element. This is what we got for AB and 50. Okay. And SL2R, so same context or same group. What is the order of A? We already said that A is infinite. You just, if you multiply this by itself, you just keep adding 1 to this upper right corner. If we view A equal to, ooh, as modular arithmetic mod, or modular, or multiplication mod P, where P is a prime. Well, based off that pattern of saying that we're just adding 1 to the corner each time, modding it with P won't affect anything until that upper right corner equals P, therefore goes to 0, which is the identity. So it's going to be order P. And since I did that in my head, I'm going to go back to the back of the book and verify it. Oh, they didn't even tell you the answer, but this is basically the instead of n we have p, and you know p mod p is 0. Okay. And saying that I'm right. Okay, 54. Ooh, got some rotation matrices. I think. Wait, what is this negative sign? Is this cosine theta minus sine theta, or is this one entry cosine theta and then negative sine theta? This is a... What? I don't actually know SPQ. They've been very specific in this book for GL and SL that if you're doing integers, you have to be mod P, or you can't be mod and not P. Or you're either not mod at all. And I don't know exactly why. There might have been an exercise about it, to be honest. Maybe you break closure or something? I don't know. Okay, yeah, you're probably right. I'm just scrolling. This is just the rotation matrix, right? It's just, I don't think they formatted it right. Like, that, okay, yeah. There's no reason for P to be prime? Okay. I mean, let's go and check how the, I don't know why the book would present it like that, but I do believe the book was saying, like, at least the book is only considering P, a prime for your mod. Oh wait, they didn't even talk about general lazy. But yeah, they, for whatever's in the book, they only care about integers mod P. I don't know why. They only want to deal with the easy fields? Okay. I think there's an exercise related to that somewhere, like considering matrices mod and not prime. I don't remember exactly where though, or if that actually did happen. Eh. Okay, so rotation matrix. I'm gonna call this a formatting error because this is so unclear to me. But I know what they're trying to say, but this minus sign is really unfortunately placed. Be a tiny bit more careful. Oh, okay. Yeah, to be fair, the book didn't say you can't do it, just they don't talk about it. I guess. So we're gonna need some to product identities, or product to sum rather, or whatever. They're saying R SPQ. They do happen to be integers, but or as for the ones up here, yeah, they're using R. It's since SL, you never get fractions anyway with integer matrices. So I assume we're gonna have to actually do some, we're gonna have to actually do this matrix multiplication out and use some trig identities. Matrices with coefficients being matrices? Wait, like, as in a matrix of matrices, or when you say coefficient of a matrix, I think that's just normal like matrix multiplication. But if the entries themselves are matrices, that's I don't even know what you do with that. Wait, but if it's to the n, how do we do that multiplication n times? I just realized this isn't as simple as I thought it'd be. Yeah, I guess it's induction. It's not a bad call, Phobos. And I was just wondering, is n equals 1 an adequate base case? I guess it is. Do you think you didn't use induction? Yeah, I wonder if you could, like, if there's some, like, binomial theorem thing that would work. I don't know how exactly that works with matrices, though. You're a renegade? Maybe there's some even, like, complex number business that you can do. But that, I mean, I'm only saying that because the stupid formatting, it looks like cosine minus sine theta. Should we think of e to the I theta, but it's not like that, I guess. You might still be able to do some kind of complex number thing, though, but it's probably not. That's probably making it more complicated than it needs to be. Yeah, it is underscore. I was just like wondering if we use that to our advantage, but I don't like immediately see it at least, so. Let's just do induction like a pleb. Yours is induction baked in, but you didn't need much since you used trig identities. Yeah, I'm pretty certain we're gonna use a trig identity here. I'm just, I guess let's do the base case. For n equals 1, it's kind of trivial to the point where I was wondering if we should start the induction from n equals 2, but I'm just going to call it good enough. I'm sometimes doing parentheses and sometimes not doing parentheses, and just try to stop me. So much writing, bro. There. Now we prove for n plus 1. Hash. Okay, finally. So I think the first good step here is to split out that exponent. With powers of matrices, are you technically allowed to put it on the left or the right? If I split out that one power, like I'm gonna do it on the right because that feels more natural. But I guess you would be allowed to put it on the left too if you were feeling inclined. Valid to start with the cheesy case? Okay, good. Oh, and I'm about to get cut off by the problem. N equals 0? That's true. Oh, positive n? Okay. We're gonna chop off the bottom half of the problem. There. You better be loud if you want addition to be commutative. Okay. So we're only looking at the left-hand side now. Now let's do this matrix multiplication. So we have cosine sine times cosine negative sine. So we get cosine squared. Wait. That makes no. I jumped the gun. We have to use our assumption and then we do. I was like, what do we do with that n? No, we have to use the assumption there and then we can do the multiplication. Oh, don't worry. You just like take the n out in parentheses here, and then you get to multiply them. That's definitely how math works. I'm gonna get cut off by the problem again, aren't I? This problem is so much writing. Goodbye, problem. Hey, warm-hearted American girl, is it ever too late to do something in life? I don't think so. I mean, if it's something you want to do, you can always do it. At least I sure hope you can. Or the world will kind of suck if you couldn't. Minus sine and theta, sine theta. We're doing good today, by the way. That'll be some trig identity, I'm sure. I think it'll be cosine n plus 1 theta, as it turns out. I'm not even going to bubble-locate the trig identities. I'm just going to assume that this is right. And it does match with my memory of how the identity works. Or it's like n theta plus theta, which is n plus 1 theta. You have that times that. That's going to match up with sine. Cosine theta, sine n theta. plus sine theta cosine theta. That times that. Minus sine theta sine n theta plus cosine n theta times cosine theta. Okay, this one if this isn't cosine n plus 1 theta, then I'm deleting my Twitch channel. That, I'm trying to mentally verify that this matches my recollection of the identity for sine. You do factor out the negative sign and the plus will match the plus. That seemed good enough to me to call it negative sine n plus 1 theta. That, for the same reason, matches. And then that matches. Okay, there. Done for the first part. You met someone in class that's 45 plus years old and willing to start a PhD in astrophysics. Oh, wow. It's very late to go to university. Yeah, I agree with underscore there. You can certainly decide that it's a big time investment and that's not worth your time, but I don't think there's like an age cutoff where you can like, or you know, the universities also have an age cutoff, and I don't think that like you as an individual should like cut yourself off. Hey Govan, how's it going? I just realized I'm not showing the actual problem. It's good to hear. So the order, how do you get the identity out of, I'm probably just going to talk through this one because I think I'll be able to get the idea. You get the identity matrix out of that when theta equals 0 or 2 pi, or any multiple of 2 pi. Or 360 degrees. It's probably easier to work with for the second part here. So for the first one, for the 60 degree case here, 360 divided by 60 is 6. And by the formula above, if you can express it as 6 times 60, that means your n is 6. So I would say this first one is order 6. The second one, they're essentially throwing a weird number at you, but I think you do the same exact process. You just have 360 divided by root 2 degrees, which is also 150 root 2 degrees, right? Or no, 180 root 2 degrees. Because you divide 360 by 2 if you rationalize the denominator. Well, that's not the order, though, is it? Is the no 150 root 2? That's not. We can't do irrational exponents in this context. How can we fix this then? This one, okay, I didn't realize this one would be a little bit more difficult. Is there some kind of identity that we can use here? Like, we don't have any ideas where we square the inside, I guess. Pre-calc trauma? Yeah. You probably go back to school again at some point year over 50. Oh, wow, $10. Yeah, I'm just thinking the order is infinite, I guess. There is no integer solution for this. It's an even number problem, so I can't go to the back of the book. But I'm going to say this is infinite order, I think. It has to be a divisor of 360. Or, yeah, it has to divide 360. And root 2 does not divide 360. Okay. Oh, I mean, that makes sense geometrically, yeah. So if you have, say, a 50-degree rotation too, if you keep doing 50-degree rotations, you're never going to get quite back to 360. Well, can you eventually? You'll still have an offset each time. Maybe that's not quite true. For an integer that doesn't divide 360. But for an irrational number, you're certainly never getting back to where you were. Okay, I think now we make a jump to 58. Isn't Pythagoras very happy if root 2 is rational? I thought the person, like, one of his followers proved that root 2 is irrational, and he threw that person off a boat. I guess that's the story that my professor told. You want square root 2 to be rational? Well, yeah, root 2 equals root 2 over 1, and therefore it's rational. I just express it as a fraction, easy. What are we skipping over though? Let's look at consider sine 58 as the next one, but I do want to quickly look and see if any of these are interesting. 55. Let's achieve the symmetry of a group of a circle. She has elements of every finite order as well as elements of infinite order. That makes sense with the rotations. Actually, it's basically the same idea as before, where every integer, or actually every rational number even, well, every finite order, can it have, no, you can't have a rational order. You can only have integer orders. So you can have elements of every integer order, which makes sense intuitively, although the mechanics of proving that are probably a little tricky. You don't quite buy the kill people. I mean, that's fair. It was like 4,000 years ago or something, so there's definitely been a lot of embellishments, or there probably have been. And the elements of infinite order are going to be irrational degrees. So I feel like I intuitively understand 55. I don't know exactly how you prove every finite order. I guess you have to do some kind of induction type of argument. Or, no, I mean, not necessarily induction. You can just prove like a general case where n is an integer. Abstract algebra. Yeah. Hey, Bladwy. All right. For 56, I guess it's really okay. Well, one more thing about 55. It'll be this is what like SPQ and underscore were saying, where you can represent every single integer as some multiple of 360 or something divided by 360. Or yeah, like if you can multiply 360 by something and divide 360 by something, I think you can make every integer with that. And I think that's, I don't know, I'm kind of losing the thread on that a little bit, but I'm still going to move on anyway to 56. In the group R star, find elements A and B such that the order of A is infinite, the order of B is infinite, but the order of A and B is 2. Aren't these just inverses of each other? No. No. It's something that is self-inverse. What is a real number that is self? There isn't. A having its arms in the air? In this context for abstract algebra, it means the order of A. And it's a little hard to describe generally. In this case, we have, I mean, this is even a good example, but it's like, if you're dealing only with multiplication, if you do A times itself, however many times you want, how many times you need to do that to get back to 1, which is the identity for R star. But the thing is, you'll never get back to 1, as far as I can tell, because if you take, A equals 2, 2 times 2 is 4, times 2 is 8, times 2 is 16, like you're just shooting off to infinity. Oh, -1, of course. Yeah, okay, that's a good point. Why do we did an A and a B that get you to -1, so we could take 2 and -2. Oh my god, Bladwy, yeah, you're so right. I forgot, -1 is a thing with order 2 in R star, and you can reverse engineer from that any A and B that you want. So A and the negative inverse of A, basically. Yeah, 2 and -1/2 work. What's up with 57? Let G be the symmetry group of a circle. Explain why G contains D sub n for all n. Huh. That's another one that makes, like, you can have any rotation you want and still be symmetric with a circle. The absolute value of -1 equals 2. Analysts won't approve. Yeah. You have to write some disturbing things when you study algebra. And that's one of them. Exactly, yeah, Bladwy. But I guess the idea for 7 is that you can rotate a circle any degrees you want, which would include every degree rotation of your dihedral groups. You can also flip a circle however you want, which will include the flips in any dihedral group you want, which I guess is the idea. That's not really an actual proof, but I think it's the idea of it. So 58 was the next one that was actually assigned by Penn Center, so I'll spend a bit more time on 58. Prove that the subset of elements of finite order in an abelian group forms a subgroup. Prove that the subset of elements of finite order in an abelian group form a subgroup. Prove that the subset of elements of finite order in an abelian group forms a subgroup. It's called the torsion subgroup. Huh. So what do we have for abelian groups? We have integer addition, integer multiplication, if they're both modded. Or if not, but... Actually, we might want not... Actually, well, they're saying prove, so the specific examples might help inform the proof, but not prove it. So we have integer addition, multiplication, and you can mod it or not mod it. Well, if you mod it, you don't have any infinite order, do you? We have matrix addition, that's abelian. We have complex number addition and multiplication, that's abelian. I don't think these examples are going to be that important, though. So, off the bat, we know E has finite order, so we can prove that this subgroup contains E and is not empty. So, up here, we showed a non-Abelian group where two finite numbers multiply, or two finite order elements multiplied to an infinite order element, which would break closure. Or, yeah, which would break closure if we tried what 58 says down there. So we must be able to use abelian to somehow show that this can never be the case. Which... yeah, I think I see how we do that. The inverses I'm not sure how we prove yet, but I think I'd see how to prove closure. And I've already answered the second part, which statement is not true for non-abelian groups by exercise 50 or whatever it was. Okay, so let G be an abelian group. Let H equal all X in G such that the order of x is finite. Now we're going to prove that H is a group, I guess by the two-step subgroup test, or H is a subgroup. So first, E belongs to G, and the order of E is 1, so E belongs to H, and H is not empty, so we can name elements that are in H. So let A comma B belong to H. Since A and B have finite order, let the order of A be n and the order of B, wait, m and n. So A to the m equals E and B to the n equals E. This means that A to the m times B to the n equals E. And since it's abelian, oh wait, how exactly does that work? I wanted to say that I want to get to AB to some number equals E, and n is finite. But I just realized it's not quite that simple because they can have different orders. Without loss of generality, let m be greater than n. A to the m times B to the n equals E implies, not that. A to the m minus n times AB to the n equals E. This doesn't necessarily help us now that I actually look at it. It's true, but not helpful, as far as I can tell. Is G over N torsion free? Well, Wikipedia's way of finding the most succinct way to disgust someone for discovering a new subject? Oh, they really do. There's a covariant functor from the category of abelian groups to the category of torsion groups that sends every group to its torsion group and every homomorphism to its restriction to this torsion group. Most Wikipedia writers are more focused on masturbation than education. Yeah. Wikipedia for math is so inaccessible. Hey, Smurfbox, how's it going? Thought maybe, oh, I like the abbreviation for underscore. You have a math problem for you? Yeah, sure, Smurfbox. Feel free to type it out there in chat or put it in my Discord, whatever's easiest for you. Okay, this does mean that a to the m minus n is the inverse of ab to the n. Oh, I don't know if that's helpful though. Is that 9x minus 7l is greater than 3 times 3x minus 7u? I might have seen this problem before, but in any case, let's go and solve that. Nine x minus 7I is greater than 3 times 3x minus 7u. Yeah, not like an imaginary number. So first let's distribute the 3 inside there. 9x minus 7I is greater than 9x minus 21u. Then we can subtract the 9x's out and they just go away entirely. So you get negative 7I. It's greater than minus 21u. And then we divide each side by negative 7, which is going to flip our inequality. And we get I heart you. Thank you, Smurfbox. I remember now, I have had this one shown to me before, but it is really like a, nice, like, problem. I appreciate you. Welcome in. So they would not have unintentionally arranged it to 3u greater than I and not understood. Yeah, the first time someone showed the problem to me, it was I'd like ask them a couple questions like, oh, like, so what's the goal here? Or like, are we trying to isolate the variables or what? But yeah, it's a cute little problem. $25. Thanks for the follow, Smurfbox. So yeah, kind of like the shtick of the stream is I take math questions from chat. I do like homework questions with things that I can actually like help with, and I solve those. And when things are kind of slow, I do. I'm studying abstract algebra just kind of out of a PDF of a textbook that I have. And I mean, you don't have to do anything you don't want to do. If you're interested in math streams in general, there's a whole list of streamers right there that I can recommend highly. And for anyone else who might be new to the stream, who's lurking. So what do I really like? What have I really done here? I feel like I've had this problem before, and there's a way to solve it. Do you, oh, maybe you have to consider like AB to the M plus, oh, yes. Okay, I remember now. And I have trouble remembering because it's a little tricky. It, like, my natural instinct is to always multiply A to the M times B to the N. But you have to do a little, like, consider in a vacuum AB to the power of M times N. Right. And we're not going to say it's equal to anything in particular yet. We're going to use the fact that it's abelian to distribute this exponent to each of them. That's not a B at all. And then we know that we can use our exponent rules to say that A to the mn is equal to A to the m to the power of n, and B to the mn is equal to B to the n to the power of m. This is helpful because we know A to the m is E and B to the n is E. So we get E to the n times E to the m, which is just E. So AB is in G. So, and mn is finite. Actually, this isn't necessarily the order of AB either, but this is good enough to show that it's finite. The order of AB is less than or equal to mn, so AB is in our subgroup is H, we're saying. Okay, so now we need to find inverses. Oh wait, this is pretty, this will be bad. If we're letting A have order m, that implies that the order of A inverse is also m. So A inverse belongs to H. Therefore, H is a group by the two-step subgroup test. Okay. So actually the closure was the slightly harder part there. The inverse part kind of follows directly from the definition of the group. Okay, what's next in the list? 59. Okay, 59. Let H be a subgroup of a finite group G. Suppose that G belongs to G and N is the smallest positive integer such that G to the N belongs to H. What? Prove that N divides the order of G. Okay, well, we can say that H certainly includes the identity. So there is all, and if it's a finite group, every element must have a finite order. which means there is an n for every g such that g to the n equals e. So you can always have n equals the order of g. But that's like, that's not the entire proof for sure. Prove that this is such a general setup that I feel like we don't have that much to latch onto here. Maybe g to the n generates h. The n divides the order of g. Okay, right. If h contains g to the n, then h also contains the subgroup generated by g to the n. And do we have something that says, like, Zone Ranger's saying to use the division algorithm? Yeah, 59 $10. So we'd have to show that r is equal to 1 if we use, or sorry, r is equal to 0 if we use the division algorithm. That's something to work with, I guess. And let's use the fact that n is the smallest positive integer so that g to the n belongs to h. R 0 is less than or equal to r is less than n. If we assume that r isn't 0, can we get some kind of contradiction or something? I guess so. Because that would mean g to the n doesn't really belong to h. This feels very weird, though. Okay, so what do we have? Actually, what's Zone Ranger saying? G to the R equals G to the order of G minus NQ. Oh gosh, okay. I would never have thought to do that. Let's try and work through these steps, I guess. Let the order of G equals NQ plus R, where 0 less than or equal to R is less than N. And Zone Ranger is saying to examine G to the R, which is R is equal to the order of G minus NQ. Is equal to G to the order of G times G to the, oops, minus NQ. G to the order of G is E, so we get just G to the minus NQ. And we know that this is equal to G to the N to the power of negative Q, which is an element of H. Okay, now this is the part where I need to look back at what Zone said. By minimality of N, R equals 0. This is the this conclusion part I'm trying to work out. So by the minimality of N, R equals 0. But this is what does the minimality of N mean here? The order of G is NQ plus R. I'm getting kind of weirded out because like R equals 0 means that this is the identity the entire time. I mean, we do want R to be 0, but I don't know, I don't think I understand this last step. Such that G to the N is an H. We got that G to the R is an H. Oh, that makes sense, Zone. Okay. So, g to the r is an h is what this says. But 0 is less than r is less than n. And n is the smallest integer such that g to the n belongs to h. So it must be that r equals 0. Okay, that makes sense. So the order of g, oh my god, the order of g is equal to nq, which implies that n divides the order of g. Okay. I would never have spotted that on my own, I feel like, but that's a nice way to do it. Like, doing the g to the r thing is it's a nice idea now that I see it. Thank you for the help there, Zone. I wonder if there's a way to do it with that whole, like, generator thing. I don't know exactly how that would work, though. Let me see what SPQ is saying. Suppose the order of g is nq plus r, with r less than n, right? G to the nq Yeah, I'm trying to understand your argument, SPQ too, because that might be a little bit more natural of a way for me to have gotten to the answer here. I probably would have just much trouble with it, to be honest. Now that I look at it, you're multiplying. I guess if g to the nq is an h, then g to the negative nq is an h. And then you're multiplying g to the nq plus r times g to the negative nq, which implies that g to the r is an h, because we're using closure for a bunch of this, I guess. And since n is minimal, by the same argument, r equals 0. Okay. Okay, so yeah, it's really just about proving that g to the r is an n, and that g to the r is really e. You're saying that g to the n generates just g? I guess, yeah. G is, huh. Interesting. Okay. Yeah, I guess I need to remember that when we're given things are a subgroup, we can kind of abuse closure to do all sorts of crazy operations and know that we're still in H. All right, so Benson are also assigned number 60 here. Let's take a look. Oh, I think I might have seen Pen Center doing this one. And the relationship wasn't simple. Like the first, like I think for A it looks simple, but then when you do B, C, and D, it's not quite so easy. I think. I guess we'll have to just do it. A matrix of groups. That's something right there, SPQ. Okay. U3, U4, U12. Poor U2. They never get mentioned here. Wait, what are we actually trying to do? Oh, the orders. Okay, let's not list out elements. We don't have to. The order of U3 is 1 and 2, so it's 2? Or, oh yeah, in the order of U4. U4 has 1 and 3, so it's 2. The order of U12 is 1, 5, 7, 11, 4. So there is that multiplication happening here. Let's see if that trend holds up. U5, 7, and 35. Five is a prime number. So we have order 4, because 1, 2, 3, 4. Same with 7. The order of U35. 1, 2. Oh god. It's gonna be 24. I may need to list these out. Well, let's try to 1, 2, 3, 4, 6, 8, 9, 11, 12, 13, 16, 17, 18, 19, 20. This is just me counting now. Not 20. Not 21, 22, 23, 24, 26, 27, 29, 31, 32, 33, 34. It's 24. Okay, so maybe this does work. Maybe I'm getting mixed up with what I saw Pen Center do. I see what's happening in chat, but let me just like go through it for myself and actually observe it, because they do give a bunch of examples, and I wonder if there's a reason they give this many examples when like 2 could have also done. All right, 4 is 1 and 3, which is 2. 5 is 4. We just said U20. It's 8. Yeah, okay, so that one checks out. What if we always have two relatively prime numbers, though? What if you don't have relatively prime numbers? 3 and 5? One, 2, 4, 6, 7, 8, 11, 13. That's 8? Okay. So it checks out for all those. Check out, it'll give us one that it doesn't check out for. In an abelian group, all subgroups are normal, so any product of two subgroups is also a subgroup. This can be defined as a regular product. I don't know how that, I guess I haven't learned the term normal yet, so maybe I just don't have, or maybe they'll get into why that actually works in the next chapter. Work out an example, z2 times z3 z4. It's kappa to be sure? Okay, yeah, I was like, I don't know what's happening there, but... Would those be like Cartesian products? Or I don't even know how to interpret that. So what happens if we had... It's like in part C, or even in part A, what if we had U2 and U6? Does that also work? There was U2 and Blondie. Wait, U2 was just one though, isn't it? Yeah. In U6, 1 and 5? So like I feel like that doesn't work for everything. Like they have to be relatively prime, don't they? Or for U20. Maybe 24 is a better thing because it has more factors. Because 10 and 2 is going to be the same issue, right? So... Oh, this is your matrix of group thing. Okay. So I'm going to say, if you have a finite abelian group, well, prime numbers don't necessarily exist in every finite group, do they? They're only saying conjecture with U, with modular multiplication for integers. So I'm going to say if R and S are relatively prime, then U of RS, the order of U of RS equals the order of U of R times the order of U of S. But if you're not relatively prime, I think you have issues. And trust me, I have plenty of issues too. You have an identity matrix with Z on diagonals? Oh god. Speaky was gonna write a masterpiece. in chat here, and I'm gonna submit it to whatever the premier math journal is. So we just did 60, so next on the list is 62. We don't have that many more that were assigned here. Like, we're coming up to the end of chapter 3. Penn Center hasn't streamed chapter 4 yet, so it might happen on like Friday or something, so we might not have an issue. But we'll see. What'd I say? 62? 62. So compute U4, U10, and U40. Oh. Okay. I think I already did this. 4 and 10 are relatively prime. So U4 is, we said it's 2. U10 is 1. What can I think? 3. 7, 9, which is 4. And the order of U40 is certainly not 8. So yeah, relatively prime. 65 is next. Let G equals ABCD as a matrix under addition. So we have integer matrices under addition. Let H be the subgroup such that all the entries add to 0. Prove that H is a subgroup of G. What if 0 is replaced by 1? Ooh. This feels like almost one of like Bode's problems. It's going to turn into do with like, we're going to have some weird manipulations that we're going to have to do here. With a whole bunch of constants being added and multiplied and stuff. But let's just go through the phases first of proving a subgroup. So I don't even know how are we gonna get the identities in H? Because the identity adds to 2, right? Oh wait, no. I'm thinking of addition, or I'm thinking multiplication. This is addition. So the identity is 0, 0, 0. So E equals 0, 0, 0, 0. 0 plus 0 plus 0 plus 0 equals 0. So the 0 matrix is an H. So H is not empty. So now we need to show closure. Okay, so this is going to be a little tedious, but let A and B belong to H with A equal to A, B, C, D. I do see the technique here. And B equal to E, F, G, H. So A plus, A plus B is A plus E, B plus F, C plus G, D plus H. I should say A times B, I guess, even though it's addition. It's abstract algebra, so everything's multiplication. A plus E plus B plus F plus C plus G plus D plus H. Let's use the associativity to rearrange this. Associativity and commutativity. E plus F plus G plus H. By the above, we know that A and B are already in H, so A plus B plus C is 0 and 0. A, B is in H. So we just proved closure here. Now we need to prove inverses. A inverse is equal to minus A minus B minus C minus D. Well, not implies. Let A inverse equal this, and then minus A minus B minus C minus D equals minus A plus B plus C plus D equals negative 0, which is just 0. So A inverse is in H. Okay. There's a little extra question to this. What wasn't there? Gunther32, thanks for the follow. Hey Waffle, there's no hydrate redeem. Yeah, those have always been a little weird to me. I don't know. I feel like I'll drink water when I want to drink water. Same thing with like stretching. I don't know. I don't feel obligated to stretch, but I see a lot of streamers have that routine. If 0 is replaced by 1, I assume we're going to break closure. Because the entries are going to add up to 2 if you add 2 things. So I don't think equals to 1 works. Of course, if other streamers want to have that redeemed, then I don't care, but I know, I've never seen the point in those, I guess, for me. All right, so we have 66 to do as well. Let H be all A and GL2 are such that the determinant of A is an integer power of 2? I need to look up my determinant properties, because I think we're going to need them here. Yeah, so if you switch 2 rows, you negate the determinant. If you multiply a single row by a scalar, wait, is B getting reduced? No. Then, okay, yeah, if you multiply any row by a scalar, then the determinant gets multiplied by that same amount. This is probably the one that we need, though. Such that B equals KA. Right. This is what we're going to need. If every row of A is multiplied by that scalar, or I assume we're going to need this at least, then you multiply by that K many times. I guess it's really an extension of this up here. So what's going on with this problem? Show that H is a subgroup. So 2 by 2 matrices, real number entries. You should have introduced the notion of a homomorphism. Would it be helpful here? We got a good long while before you get to homomorphism, unfortunately. Determinant GL2R to R star is a homomorphism. Oh. So we do have, so the identity is 1, 0, 0, 1, just the regular identity matrix. And that is a power of 2 because the determinant is 1, so 1 is a power of 2 technically. The allowed values of det are the subgroup generated by 2. Oh. Yeah, okay, yeah, that makes sense. Are therefore inverse determinant? I don't know that pre-image. Oh, wait. Maybe not inverse, but pre-image? I don't know how to interpret that notation because I haven't gotten there yet, but okay. It is a pre-image. The pre-image of a subgroup under a homomorphism is a subgroup. Okay. Pre-image of the subgroup generated by 2 under the operation determinant. Oh, I guess, yeah, the determinant, you can think of that as a function mapping matrices to real numbers, can't you? Okay. Oh, okay. If I accept what you're saying is true, I think I understand that. That's kind of neat, to be honest. Unfortunately, we don't get to use that tool, but that is good to know. Kernel preimage of 0. Known as the kernel is also therefore a subgroup. I don't remember what kernel is, or I think I remember kernel in the context of linear algebra is. But I remember seeing you and others talk about the kernel in this abstract algebra stuff, and I don't know what that is. Or maybe I learned about kernel in the context of abstract algebra, I just don't remember it. I don't know. The only kernels I appreciate are popcorn kernels and the kernel of an operating system. In the kernel of an army. That's not the same kernel. Basically the same, the preimage of a trivial subgroup. Oh, okay. So first off, we want to show that, what are we using to call the subgroup? H. The determinant of 1, 0, 0, 1 is equal to 1, which equals 2 to the 0. So the identity is in H, and H is non-empty. So now we can let A and B belong to H, which means that A equals 2 to the M, and that B equals 2 to the N. Sure. So if you multiply how's this going to work? What happens to the determinant if you multiply two matrices? I don't think I looked at the right determinant property, actually, now that I look at it. I was thinking, like, maybe try to somehow express matrix multiplication as, like, scalar. stuff. Can we still do that? Do we have to go element by element? Oh, never mind. Okay, this just does the work for us. Okay, glad I looked back at this. The determinant of AB is equal to the two individual determinants multiplied. That makes life much easier. My linear algebra kind of sucks, by the way, so I have to look all this up. So we've just proven that the determinant of AB is equal to the power of 2 still, so we know that AB is an H. Now we just need inverses. Is there another property for inverses that does all the work for us? I feel like there should be. That's transpose. Haha. This does all the work for us. 1 over a power of 2 is still a power of 2. The determinant of A inverse is equal to 1 over 2 to the m, which equals 2 to the negative n, which is still a power of 2. So A inverse belongs to H, and we're good by the two-step subgroup test. What? Oh, no. Okay, there we go. If an alert happened right then, it would have been off the screen because I accidentally dragged the wrong window in my OBS. We just did 66. Let's do 67. Let H be a subgroup of R under addition. Let K equals 2 to the A where A belongs to H. Prove that K is a subgroup of R star under multiplication. Ooh. So, you know, this feels like it's hinting at homomorphisms. That's what I think when we're like switching between sets and operations. K equals 2 to the A, or A, I mean, I don't know. Is H even that important here? H is just every integer, right? Oh, it's a subgroup of R. Never mind. So I'm making this too simple. It's R, not like integers. A subgroup of R under addition. And K is 2 to the power of that subgroup. Oh. Oh. Log base 2 is a homomorphism from R r star to r plus, or for positive r's with multiplication to all r under addition. Okay, yeah. We had an algebra contest. I know it's directed towards SPQ, but I'm curious to see too. We had an algebra contest preparation a few months ago. The subject introduced traces on a general ring A. Which has to manipulate the trace of matrix C with coefficients A. Okay, yeah, I don't get it. I've heard of the traces of a matrix. I didn't know they exist for rings in general. So transferring from addition to multiplication, I'm trying to grapple with the meaning. So what is the set? Like, I guess we need to figure out, like, what is K? So I guess, like, what subgroups, or I guess what are the possibilities for H before you even think about K? Like, what is a subgroup of R under addition? You could add, like, only even numbers. I guess you could add, like, you know, any multiple of a real number R. Oh yeah, SPQ. I figured you're saying the reverse direction or something. Um, so or H always includes 0, the additive identity. So K always includes 1 because A can be 0. So K is always going to include 1, the multiplicative identity. So we just shown that K is non-empty. That seems like progress. So we can make the claim that 0 belongs to H, which implies 2 to the 0 equals 1 belongs to K. Oh my god, that's not a K at all. So K is non-empty. And it definitely includes the identity. Now, I guess we let A and B belong to K? I'm just blindly following the steps here. We want to prove closure. So A is equal to 2 to some power, and B is equal to 2 to some other power, and M and N belong to H here. So we want to prove closure, so we should multiply A and B. So since H is closed, I guess this is doing the work for us, really. M plus N belongs to H. So 2 to the M plus N belongs to K. Okay, that's not as bad as I thought it'd be. Now we need inverses. Observe that negative M belongs to H. So 2 to the negative M belongs to K. 2 to the M times 2 to the minus M equals 2 to the M minus M equals 2 to the 0 equals 1 equals E. So every element A has an inverse in K. Okay. That's not as bad as I thought it'd be. I think I'm gonna maybe call things there for the day, though. Actually, let me bring that up. A little slow today, but we did get some good algebra-like progress in here. Oh shoot, I'm not gonna solve 69? Should I? Oh, I mean, are you just memeing? 69 is a sign, so I'll do it at some point. What does 69 say? Oh, I remember seeing Penson do this, and I remember like instantly figuring out the answer, but now I can't instantly figure out the answer. I think not, because inverses break. Yeah, I don't think H necessarily, or like this one doesn't necessarily have an inverse with non-zero integers. That's why you have to put a constraint on the determinant. Actually, well, it's GL. But no, you don't necessarily, you might have a rational number A and B for your inverse, so. There you go. I don't see any of the usual people I would raid. I don't have any of my follow list who's on. Let me see if there's someone random who we can raid though. If not, I'll just end things. Actually, let me cut the YouTube stream off here. Goodbye, YouTube.